Good day, class, and welcome to our 10th lesson in organic chemistry. Today, we are going to be treating carbonyl compounds. Carbonyl compounds are aldehydes and ketones. The carbonyl group, that's the carbonyl group, C double bond O. That is, both the aldehydes and ketones have this carbonyl group. Aldehydes and ketones, as such, are similar in that they both possess the carbonyl group. Aldehydes have the general formula RCHO, while ketones have the general formula RO1CO2. Where RO in both cases, that is, in both the ketones and aldehydes, may be an alkyl or aryl group. RO1 and RO2 may be or may not be the same. The difference between aldehydes and ketones is the position of the carbonyl group. For the aldehydes, the carbonyl group is situated at the end of the molecule. That is, you can take for example methanol. You see that with methanol and ethanol, the carbonyl group is being situated at the end of the molecule, while for ketones, the carbonyl group may be located at any point or anywhere along the molecule. For example, propan-2-on. You see that the carbonyl group is situated at the second carbon, the middle of the chain. In naming the ketones, the position of the carbonyl group must be emphasized. The aldehydes are terminal, while the ketones are not terminal. The carbonyl group is highly polar, so dipole-dipole forces between the molecules are quite significant. These dipole-dipole forces between the molecules leads to high melting and boiling points of the carbonyl compounds than alkanes of comparable relative molecular mass, but not those of alcohols where hydrogen bonding occurs. What we're trying to say here is this, that the melting and boiling points of aldehydes and ketones are higher than those of their comparable alkanes, but the melting and boiling point of aldehydes and ketones, that is carbonyl compounds, are lower than those of the corresponding alcohols. The next thing we'll be looking at is the physical properties of carbonyl compounds. Except methanol, all simple carbonyl compounds are liquids at room temperature. The earlier members of both series are considerably less volatile than the alkanes of corresponding relative molecular mass. For example, methanol with boiling point minus 20 degrees Celsius is a liquid at room temperature, while propane with same relative molecular mass is a gas at room temperature with boiling point minus 40 degrees Celsius. This is because the oxygen molecule of the carbonyl group makes it possible for hydrogen bond formation between the molecules, while in the case of propane, the weak van der Waals forces can easily be broken. The polar carbonyl compound has less effective on intermolecular forces. That is, the polar carbonyl compound has less effect on intermolecular forces than the hydroxy group. And you know the hydroxy group occurs within the alcohol. This is because the hydroxy group has a higher tendency to participate in hydrogen bonding than the carbonyl compound. Thus, the boiling point of methanol, though higher than that of ethane, is less than that of ethanol, whose boiling point is 78 degrees Celsius. That is, we mean that the boiling points of carbonyl compounds are lower than the boiling point of alcohols, but the boiling points of carbonyl compounds are generally higher than the boiling points of the corresponding alkanes. Lower carbonyl compounds are soluble in water as a result of the solubility. Lower carbonyl compounds are soluble in water as a result of the ability to form hydrogen bondings. That is, they form hydrogen bond in water. That's the molecules of the carbonyl compound with the molecules of water combine together to form hydrogen bonding. Carbonyl compounds dissolve both polar and non-polar solutes. They dissolve polar solutes as a result of the polarity of the carbonyl group, and they will also dissolve non-polar solutes because of the non-polar nature of the alkene or aryl groups. For example, propanol is a widely used industrial and commercial solvent because of its ability to dissolve both polar and non-polar solutes. Solubility of the carbonyl compounds decreases as the aryl groups increases in size. And remember, we said the aryl groups represent either the alkene or aryl groups. The next thing we're going to look at under the carbonyl compounds is going to be the reactions of carbonyl compounds. We see that carbonyl compounds undergo oxidation reaction, combustion reaction, reduction reaction, whereby they are being reduced using either lithium aluminium tetrahydride in dry ether solution followed by the addition of water or nickel. In their combustion reactions, they burn in excess air to form carbon dioxide and water. And you can see from the reactions there, you see that propan-2-on burns in excess oxygen, that's 4 molecules of oxygen, to yield carbon dioxide gas and water liquid. Propanal also reacts with oxygen, it burns in oxygen to yield carbon dioxide gas and water. Going further, we're looking at their oxidation reactions. You see that aldehydes are readily oxidized to carboxylic acids when treated with acidified dichromates. Aldehydes when treated with acidified potassium dichromate, and dichromate is an orange color. As such, when they react with aldehydes, they form carboxylic acid and changes the color of the dichromate from orange to green. Ketones are not readily oxidized to carboxylic acids with same number of carbon atoms. The next is their reduction reactions. They are both reduced to alcohols. Aldehydes are reduced to primary alcohols. Ketones are reduced to secondary alcohols. They are reduced by a variety of reagents. The first reagent we're looking at there is being reduced with hydrogen and a catalyst of nickel or platinum. You see that ethanol in the presence of hydrogen and nickel catalyst is going to yield us ethanol, that's a primary alcohol. Propan-2-on is being reduced with hydrogen in the presence of nickel catalyst to give us propanol, that is a secondary alcohol. To be precise, propan-2-ol. The second method of reducing the carbonyl compounds is by using lithium aluminium tetrahydride in dry ether solution, then addition of water. As you can see there, ethanol being reduced is going to give us ethanol, which is a primary alcohol. And the next method of being reducing is by Clemsen's reagent. Clemsen's reagent is amalgamated zinc and concentrated hydrochloric acid. This tool reduces all classes of carbonyl compounds to hydrocarbons. That is, it reduces the carbonyl compounds to their corresponding alkanes. For example, ethanol will be reduced in the presence of 2 hydrogen ions to give us ethane. Propan-2-ol undergoes same reaction and is going to form propane. Now we're going to be looking at their addition reactions. They undergo mainly nucleophilic addition reactions. As you can see from the general mechanism there. Like I always say, an arrow generally moves from a negative pole to a positive pole. As you can see there, the carbonium ion, which is positive, and the X ion, which is negative. You see that there's an arrow moving from the X ion to the carbonium ion. Also, an arrow moving from the oxygen ion to the Y ion. Note that X represents nucleophiles, while Y represents electrophiles. Addition reactions of carbonyl compounds are influenced by 2 factors. The first factor there is a positive inductive effect. Aldehydes have faster reaction rate than ketones because aldehydes have only 1 arrow groups, while ketones have 2 arrow groups, which tends to reduce the positiveness of the carbonyl carbon atom. Thus, the alkyl or aryl groups exert positive inductive effect. That's positive I. The next one is going to be steric hindrance. If the substituents on the carbonyl carbon atom are large, then they tend to show low nucleophilic attack. That is, they tend to slow down the nucleophilic attack on the carbonyl group. This slow rate is due to the steric hindrance of the groups attached to the carbonyl carbon atom. Like you can see here, you see that, and you can see that you're going to see that due to steric hindrance, moving from methanol to ethanol, then to propan-2-ol or any of the ketones. See that the more alkyl groups are being attached to the carbonyl group, it reduces the reactivity, it slows down the rate of reaction, meaning that methanol is more reactive than any other aldehyde, and aldehydes will be generally more reactive than ketones because ketones have 2 arrow groups attached to the carbonyl group, while aldehydes have just 1 arrow group attached to the carbonyl group. Within the aldehydes, methanol is the most reactive because it has no arrow group attached to the carbonyl group. The first addition reaction we're going to be looking at is addition of hydrogen cyanide. They react with hydrogen cyanide in an alkaline medium to form 2-hydroxy-alkanonitrile. The hydrogen cyanide is usually generated by the action of dilute sulfuric acid on the appropriate metal. that is the appropriate metal cyanide. For example, you could use potassium cyanide or sodium cyanide. Like you can see from your screen, the end reaction. You have ethanol undergoing the addition of hydrogen cyanide in the presence of potassium cyanide and sulfuric acid, that is dilute sulfuric acid, at 10 to 20 degrees Celsius to yield 2-hydroxypropanonitrile. We have propan-2-on undergoing same reaction under same conditions at 10 to 20 degrees Celsius in the presence of potassium cyanide and sulfuric acid to yield 2-hydroxy-2-methylpropanonitrile. In the addition of sodium hydrogen sulfide, they react with excess sodium hydrogen sulfide at room temperature to yield alkyl sodium sulfide. Aldehydes react more readily than ketones because ketones have two aryl groups attached to the carbonyl carbon, which reduces the positiveness of the carbonyl carbon atom, that is, steric hindrance. Note that in the addition of sodium hydrogen sulfide, the reaction of aldehydes with sodium hydrogen sulfide is being completed at 87% at 25 degrees Celsius under 30 minutes. Meanwhile, for the ketones, the reaction is being completed to 47% at 25 degrees Celsius in 30 minutes. The next reaction we're going to be looking at is the keto-enol tautomerism. It takes place in aldehydes and ketones with alkyl hydrogen atoms next or adjacent to the carbonyl carbon atom. It is promoted by either hydrogen or hydroxide ion. That is, it is promoted either in an acid or an alkaline medium. Whether in an acidic or alkaline medium, the isomeric forms exist in equilibrium. Since the two isomers are in dynamic equilibrium, they are called tautomers. As you can see them, you have a propan-2-on, which is the keto isomer, undergoes the keto-enol tautomerism to give us enol. Enol has a hydroxy group attached on the second carbon atom. We have the second equation there, propanal, which is the keto isomer, undergoes keto-enol tautomerism to yield enol, whereby the hydroxy group is being attached on the first carbon atom, that is, the primary alcohol. In our next lesson, we are going to be looking at the condensation reactions, which are otherwise known as the addition-elimination reactions, whereby there is an addition and there is also an elimination of either a compound or an atom or group of atoms.